Hi everybody, I'm Vincent. In this video I'm going to present research I conducted with my advisor, Dr. Brent Hecht, that studies conscious data contribution, a way for users to exert data leverage against tech companies. Alright, so the backdrop for this work is that there's a growing concern about the serious negative societal impacts of data-driven technologies operated by large tech companies, both in the media and in academic communities. Intelligent technologies have been linked to economic inequality, which is itself associated with many societal harms, but also increasing attention has been paid to the ways that tech companies may be harming privacy and democracy, among other concerns. Attempts to exert leverage against tech companies to kind of try to maybe stop these behaviors, say through consumer protests like boycotts, must contend with the market power wielded by large tech companies. So in our paper, we introduce and explore the data leverage concept. And data leverage is the power to influence a tech company held by those who implicitly or explicitly contribute the data on which that tech company relies. So one way of exerting data leverage is through data strikes, when users withhold or delete data from a company that they wish to exert leverage against. So we studied data strikes through simulations in a 2019 web conference paper. And then an alternate form of data leverage, which we focus on in this paper, is conscious data contribution, where users give data to a target's competitor. So the idea of data leverage builds heavily on an earlier concept, data as labor, and a variety of work studying data as labor has highlighted that users of tech companies play a crucial role in generating valuable training data to fuel intelligent technologies. This so-called data labor is a huge component of the success of all these data-dependent technologies. More generally, any case in which tech users, the public, generates or contributes to data used to train intelligent technologies can be seen as an instance of data labor. So indeed, for many tech companies, all their users are simultaneously data laborers and consumers, and both roles are contributing to company profits, so both roles are potential sources of leverage. So anyone who engages in data labor also has the capacity to withhold this data labor. Laborers who withhold their labor as part of a strike get to gain leverage. And this means that data laborers can withhold their data labor to engage in a data strike to gain leverage. So data strikes are potentially very effective. In our prior work, for instance, we found that a data strike by 30% of the users of a small recommender system could take that system's performance halfway towards the unpersonalized baseline. However, data strikes must contend with the diminishing returns of data to machine learning systems. So a system with a billion data points is unlikely to see much of an impact from a small data strike from just 1, 100, or 1,000 people. Furthermore, a user who participates in a data strike hinders their own ability to benefit from ML systems. Someone who deletes or withholds their data will receive only unpersonalized results from any personalization systems that they try to use. So that's where conscious data contribution comes in. Imagine we have some participants, a group of users who share some concern about a tech company's values or actions, and their target is this company, LargeCo. So they could try to cut off their data contributions to the target as part of a data strike. Maybe this data strike is too small to create a noticeable impact. However, let's imagine that there exists a small tech company, a small co, with similar services, and small-co's values and actions are in alignment with the participants. So what the participants can do is they can contribute data to small co to boost up the performance of small co's tech and in turn create more competition for large co. So to situate CDC, we can think again about existing tactics for getting leverage. So the data strike framing is inspired by labor strikes aimed at exerting leverage against an employer. CDC draws on conscious consumerism, a tactic aimed at rewarding a company. So at the same time, CDC can exert leverage through increased competition. To illustrate, let's consider a simple example. Here's a plot of the relationship between machine learning test accuracy on the y-axis from 0 to 1, and then what fraction of a data set is available. So we see here this curve with a diminishing returns, kind of flattens off at the end. And a critical thing here is, so let's imagine that 20% of users delete their data as part of a data strike. This would basically have very minimal effect on the classifier performance because we're kind of in this flat region. However, if 20% of users engage in conscious data contribution, CDC, and give their data to a new small company, they could bring that small company's performance from 10%, the random guess baseline, up to 80% accuracy. So CDC hugely reduces the performance gap between the two companies. All right, so going a little bit more into detail about our simulations in the paper, I'll start with the premise. So we define two companies, LargeCo, the target of protest, and SmallCo, their competitor. And we assume that SmallCo starts with no data, while LargeCo starts with a full data set, 100% of the benchmark data set from other ML literature. And we're going to say LargeCo is going to lose data from a data strike, while SmallCo gains data from conscious data contribution. And we consider three scenarios. So we have participants only data strike, participants only engage in CDC, and then a third scenario in which participants jointly engage in a data strike and CDC. So they delete data from large co while giving that same data over to small co. So the purpose of the simulations is to see how much our imaginary large co's performance decreases and how much small co's performance increases. Then we can compare the relative effectiveness of data strikes and CDC in terms of kind of closing that gap and exerting leverage. So the simulation effectively follows the procedure used to study learning curves in machine learning. You take a sample of the data, you retrain from scratch, evaluate performance, and kind of do that over and over again until you build this learning curve. So in order to compare the effectiveness of data strikes and CDC with different size participation groups, we defined a measurement, data leverage power, or DLP. So to compute DLP, we first identify the baseline performance. So that's like the performance of a random guess, for instance, or recommend most popular. And then also the best case performance. So what's the best performance reported in prior work? And then for each ML use case, we assume small co starts at that baseline, that worst case, and large co starts at that best case. So a quick summary is that higher DLP means that data leverage participants have more leverage. DLP of 0 means no effect at all. DLP of 1 means that data leverage either boosted small co all the way up to best case or dragged large co all the way down to worst case. And DLP is basically just a linear transformation of a relevant performance metric that machine learning researchers would use. So like root mean squared error, accuracy, precision, etc. More details in the paper, but I'll also talk a little bit more about it here as well. So for CDC, we basically are looking at what's the fraction of the way from baseline to best case that the CDC brings small co's performance. For CDC plus data strike, there's a wrinkle here because now we're looking at what fraction of the way from baseline to the data strike inhibited performance did CDC take small co's boosted performance. And then for a data strike, we're just looking at what fraction of the way all the way up from best case down to worst case did the data strike bring it down. And again, the paper has a lot more details on exactly how this is defined. So why are we doing all of this? Well, DLP is agnostic to ML evaluation choices, so we can kind of compare different tasks, even if one uses root mean squared error and another has classification accuracy. It lets us compare data strikes and CDC in a really nice, simple one metric fashion. Of course, it is really important to consider the underlying metrics like classification, accuracy, and ideally we really want to also look at the relationship between performance and real-world outcomes. So like what's the financial cost of a false positive? This is really hard and probably requires some proprietary data or kind of collaborating with firms. So this is an area for future work. So to select use cases for study, we sought out well-studied tasks with publicly available high-performing implementations. And there's 4 basically. So it's recommendation with movies, recommendation with Pinterest items, classification of images, and classification of text. And I recommend checking out the specific references in the paper for more detail. So here's a slide now showing our experiment results for a single use case, movie lens, movie recommendations. So the left-hand plot is showing DLP. On the y-axis, we have DLP, which goes from 0 to 1. 0 being no participants, 1 being maximum number of participants. And the x-axis is showing that participation rate. So bigger means more people are joining the CDC campaign or the data strike. And the right hand is showing the underlying performance measurement, in this case, root mean squared error, from which we calculate DLP. And here we can see that as participation goes up, large co loses data, RMSE gets worse, goes higher, and small co is getting more data, and thus a lower, better RMSE. And basically, we're seeing exactly the same diminishing returns that we might expect to see in many machine learning and statistical contexts. So looking at a similar plot for all 4 cases now, we see the results are actually quite similar. We see that deletion-only data strikes have very little DLP until large participation is achieved, where CDC scenarios have very large DLP with small participation. In other words, CDC is kind of taking advantage of this very vertical part of the diminishing returns curve. So just to zoom in on a specific example, in the movie lens case, 50% of users get small co over 90% of the way to best case. Pinterest, 20% of users get small co over 90% of the way to the best case performance. And we see that the exact fraction of users to get performance up to some threshold is not the same in every context. In general, the trend of a small or moderately sized group being able to achieve these really large improvements in performance relative to the starting point baseline is very consistent across all of these kind of very different contexts. So now, just as a discussion point, I'll note that CDC can help change the narrative around the power dynamics between tech companies and the public. The idea of protesting large tech companies may seem very hopeless, but we believe that CDC can even the odds a little bit, allowing a small group to actually have an outsized impact. With that, I'll end the presentation with a huge thank you to my advisor Brent, as well as the huge number of folks who contributed to the software, the data that made this work possible. Thanks to all the reviewers and my many colleagues who provided extremely helpful feedback. And some contact info I would love to chat more about with you about this research. Thanks so much.